I'm going to be the chair for the next two talks. My name's Andy Goetz. We're moving on to an area which is maybe hasn't been addressed up to now, but is about using machine learning and deep learning, artificial intelligence techniques. I think there's going to be a lot of there's a lot of potential here for the work that you're doing, because some of it's very time-consuming.
And can I just move through?
We had a workshop here 2 months ago, which was very successful. You can still find all the talks online, so if you want to have a look about applying machine learning and artificial intelligence to photon and neutron science. So the first speaker is James Brusuelas from Kentucky, and he'll tell us some more.
Thank you. Thank you for inviting me. So yes, I'm James Brusuelas from the University of Kentucky, and I represent a larger research team led by Brent Seals. And like most of the teams evident here, we truly are an interdisciplinary team in what we're trying to do. And we're very interested, like most people here, in extracting non-invasively content from, well, it's just hidden and trapped inside damaged culture artifacts, in particular one that has come up many times in this conference. The Herculaneum papyri scrolls. With a lovely introduction to the background, the eruption of Vesuvius, I fortunately don't have to go into all that. We can kind of stay on time here, and just looking at the variety of intact scrolls and also open fragments. But really, it's getting into that this intact scroll is the big problem and the large challenge. For our virtual unwrapping, I'm sure most people are familiar with the fact that, yes, we have a nice process for virtual unwrapping, and this was successfully applied to the carbonized parchment scroll from Ungetty, in which Dr. Seals' team, before I actually was hired and brought to Kentucky, did successfully virtually unroll it, and that text was deciphered very quickly as a text of Leviticus. And in this sense, I think we're all familiar with the fact that the iron gall ink is largely the culprit for why we could read this so clearly. It just readily appeared in the tomography. So what I'm going to talk about today really is the kind of the logic behind the deep learning approach that we've been experimenting with. And this comes down essentially to our concept, or just the concept of the morphology of what we're dealing with here. And this image here, just papyrus, inked papyrus under an electron microscope, what we're trying to isolate is the structure here. We can see the papyrus and we can see the ink. There it is again. Now what I'm about to show you here is just more close-ups, is a oversimplification of the process, but it'll kind of convey what's going on here. So in this instance, if we have our raised surface, which is our fiber, basically whether it's iron gall or carbon, it gets applied, it sits on top, but also soaks in, and this is essentially the signal that we're going for in applying deep learning. Now, in the case of Ungetty, when you get it under the tomography, it's bright and it's legible, and so it's mostly, it's going to look like this. Problem with carbon is that usually every time we try this approach, this is essentially what we're getting, right? The fibers are there, but nothing is there. But what we're really focusing on is the fact that it isn't invisible. It is there. It's just coming up with the recipe, the cocktail, so to speak, to find that signal, isolate it, and amplify it using deep learning and artificial intelligence, whatever we wish to call it. So our emerging principles here are the morphology. The ink as a layer on the substrate changes the shape of the surface. That's the signal. But we need to capture the micro-CT at a high enough resolution to show this ink evidence, to tease it out, something to lock onto. And this is our process of deep learning. Going to the carbon phantom, we're just going to kind of walk you through the general process of starting up the test scenario, the training scenario, based on our phantom. Here we've got 6 columns, and this represents essentially thickness of ink, starting with 1, just 1 pass of carbon ink. 2 increases the amount of ink over and over and over again. You can see that the thickness increases by just looking at the Greek letter shapes. That delta or the theta or the sigma just gets thicker over across. And we also have our numbers, and we got our bullet points, which are in iron gall. As an example here, we get our expected result, right, if you put it in tomography. And column 2, can't really see it. We can see the 2, we can see the points because those are iron gall. Middle, we just have the phantom. And 3 represents the creation of labels, creating the masks, creating the training labels, because now what you're going to do is you're going to create these because of where you know where you're at, because of that iron gall. You know that that ink has to sit in there. So this is how you create those training labels. And it's an iterative process over and over and over again, with the critical fact being, at the end of the day, to really assess your deep learning algorithm, your AI approach, is how good is it at predicting across something it does not know or it has not seen. So it's essential to have that leave one out. The overall process here that we're looking to insert this method into is just basically this. We got our volume, we acquire the CT, we apply the virtual unwrapping pipeline, we align to reference, we create these labels. What we're looking for here, essentially at this stage, if you want to think about what the machine knows, what the machine does not know, how is it learning, what is it thinking about? Right now, it's really just thinking in the confines of ink versus no ink. Here's our phantom again. Here's the entire phantom under the CT. Now, what's interesting here is, yes, you can still see all those dots, you can still see the iron gall, but if you really look closely at the image, the thicker the strokes, the more times we took that pen and wrote over the delta, wrote over the sigma, and increased it, made it thick, the ghost actually almost seems like it starts to appear. What you're looking at here is a result of the convolutional neural network based on how it's trained, based on all those labels, going over those sections, and then also going to the point of leave one out, pass it over something it does not know. Here we can see that just standard one stroke, just write delta once with the ink. It does have problems. It can't really tease it out. It can't find it. It's not differentiating ink, no ink. Go down the rows. Yes, the thicker it is, it can latch onto a signal, and that signal can be amplified to tease that stuff out. We even did simple tests in the sense of, well, let's just not focus on ink at all. Let's just look at the RGB. Have the convolutional network think in terms of, can it predict and classify black versus tan with the carbon phantom? What you get at the end of the day with the output solely based on this carbon phantom and the training labels that were created is you can generate this. And what's critical about this image is that it is a generated image from the output of the neural network. So what we understand here is that yes, using this approach, you can train you can apply deep learning to basically take that CT scan data, latch onto that signal, amplify the letter shapes, and create a photorealistic representation. What's also interesting here is it's not even so much just the letter shapes. If you look closely, it is identifying and picking up on the pattern of the fibers themselves and doing a decent job at recreating that as well. Just a kind of an overview of what you've got here with this essential training based on our phantom. Top row, we got the phantom, we have the CT, we've got the output of the neural network, and then this photorealistic regeneration of it. What it's coming down to in the minds of our computer scientists, I am actually digital humanities papyrologist classicist. I'm not a formal computer scientist, even though I tend to absorb, and I am absorbing more and more just working with this team, is that it's often explained as a resolution, almost a numbers game. At what resolution do we need to be to isolate that morphology, to isolate that signal? Right now, based on our research, we're kind of thinking that you probably need to be somewhere in the range of probably at least around 10 microns, somewhere between 10 to 2, maybe 3 microns, to where we can hope that we can actually have this deep learning approach that can latch onto that signal and start to amplify it. We did recently, back in September of last year, go to Diamond Light, the synchrotron there out in Oxford, to do some scanning with the P-Herc scrolls from the Institut de France. Here's a nice image of Brent and Madame Berard. Now, what also should be noted here is that in doing this research in general, for us, it's not just working at the level of how to apply the computer science methods, the deep learning methods, digital humanities methods, papyrology. There's a level of conservation that goes in, that's involved here, because to get these scrolls, and in this instance, the I-12 beam, we do actually have to create custom cases so that we can mount them in the beam. And these are simply, well, not simply, these are created using photogrammetry to capture the topography of the idiosyncrasy of each scroll, and then basically 3D print them out so that they can be placed inside very carefully and mounted in that beam. Now, the diamond data is just coming to us. We're only now at the stage of beginning to process and play with the reconstructions, but we do have some images, fortunately, to show you here today. So here's basically Paris 3 at 25 microns, 8 microns. There's some close-up shots. Again, conveying that right now, for the approach that we're taking is we need to get in there at the resolution that we think we require for the deep learning method to work. Let's see if it's stuck. Come on. Oh, and finally, here's just some vertical slices I wanted to show you as well. And we got some nice animation video to kind of show you the internal structure. It's going to look kind of like what we're already used to from prior imaging. It looks just like it's a mess in terms of thinking about how to go about segmenting that in the end. But that's part of the fun. So this engine for discovery, this idea of getting in there to really truly extract mass amounts of text, to actually read text, identify text locked inside these intact scrolls. It's going to be a process of acquisition, segmentation, texturing, but with the texturing, putting a layer of deep learning on it to actually extract that text. And then, of course, flattening, merging, and then ultimately reading, scholarship on these texts. What I'm going to end with here to kind of convey further the process, the reason why we're pushing and following this path, is right here. This is Object 59, which also belongs to the Institut de France, which was just put in a conventional SkyScan CT scanner at UCLA last year as well. Now, because it is an open fragment, because there actually is ink on the top, this is an opportunity to basically test the deep learning process from another angle, because we truly believe the way to really unlock all of that text inside is going to require the open fragments to provide you the training data that you ultimately need. So what we have here is just, again, looking close up, what we kind of expect for the Herculaneum fragments under CT scan conditions. But here, what we're going to do in this experiment, and some of you may have seen this because Dr. Seals has presented this somewhat recently, back in October at the Getty. We split this in half, where we used the left side as the training side, and we used the opposite side to classify, run it over something it hasn't been trained on. So what we're looking at here in the video that we're about to show is we're looking for the amplification of a Greek letter roughly the size of this delta. And as somebody that does read Greek and as a papyrologist, I can categorically tell you that yes, I do see the amplification of the omega, which is there. So where we're at now with, and I'll wrap it up, keep us on time. What we're at with the diamond data is it's not just immediately throwing the deep learning process as it currently exists at that data, mainly because that data is immense. The sheer size of it not only requires, well, it requires us to basically refine and keep working on the existing tools because of, it's in, I forget how many terabytes that data is, but it's large. And so right now it's an exciting moment because we're now getting it and we're going to start to basically throw what we currently have at it to see what the process is going to be down the road for applying our method to start fully extracting large amounts of texts from something either under a layer, hopefully, if we actually apply some of these methods to open fragments, but really getting at those intact scrolls. Thank you.
Questions? Any questions?
Too impressive, Anna.
I have a color question. In some of your letter, I saw the letter identified in white, sometimes in black. I guess that the color map is the same.
Yeah, well, so basically this is an instance of you code within the algorithm itself what color you want it to actually pop up. So why you're seeing it is basically you're seeing it white because we basically are having it amplified in that.
No, I understand, but is more absorption white or is less absorption?
Don't
is
know if I'm
white is
following
more
you.
absorbing, so let's say lead, metal that absorb more? Or?
Well, in this instance, we're not really. Yeah, it's not. The process right now isn't based on absorption. Right now, the process is based on training the machine to understand at the level of resolution that we have what is papyrus and what has changed the topography on top of it.
I understand the algorithm, but your rough data are essentially radiography, tomography, etc. So if you use the same color map, white should be more absorbing or less absorbing. After you can have any algorithm you want to enhance signal, but it's more absorbing than background or less absorbing than background?
I don't know if it's at the end of the day that what the question I think you're asking doesn't apply to the technique that's been applied. It's not that it potentially cannot and not have influences on adding to it, but right now we're not. Well, the machine isn't thinking in terms of absorption.
No, I understand that the machine does know, but physics behind should know.
I don't have a response at that at this time then.
Thank you.
I had a question, which is, what is the most time-consuming part of this process? Is it the segmentation or the?
It's probably a little bit both. I think at the end of the day, for the intact scrolls, the segmentation will appear just as challenging as the amount of time that has gone into the deep learning method.
And have you thought of applying deep learning to segmentation?
Yeah, so we're also we do have students that are working on the process of automating segmentation, because at the end of the day, when you look at that volume structure, that internal structure, to do it manually by hand just doesn't seem very appealing. And for sheer accuracy, the amount of times it's going to have to go over to get that segment out, we would prefer to have that automated.
Yeah.
But again, because of the sheer size of the data based on the resolution, it requires another level of iterating on the code, on the algorithms that you've already created to get it to work properly down the road.
Are we talking of years? Yeah.
No, well, I couldn't put a finger. I won't come out and guarantee you when it's going to happen. But what I can say is I think we feel confident that we're on the track to, in a very timely fashion, hopefully, start to extract large amounts of text from basically like a bit of segmentation. But when you can do it an entire scroll, that I do not know, and that will take much more time, I think, down the road. Because it depends on the internal structure. Not all intact scrolls are basically going to be the same in terms of how they were damaged. So you might find one that, for whatever reason, doesn't have all the bumps and bruises, all the contusions and contortions. And so it becomes a better case for virtual unrolling because of that circular circumference structure is still kind of there. So segmentation process can go faster. But as soon as you look at something that looks like a rat's nest or like a bunch of strands of jewelry like thrown together and you got to peel it apart, that's painful.
So it means eventually we'll come true, we'll read the whole scroll.
That's the idea. That's the idea.
Yeah, okay. Thank you. Yeah, I was interested to see, in addition to the actual relief that you're going to get by the ink, you will also get a contrast between a kind of textureless surface left by the ink and a fibrous surface of bare papyrus, right? Is it going to be able to pick that up?
Yeah, so that's also on the list with the new Diamond data, is improving our methods for looking at what's in the neighborhood, right? Mm-hmm. Because the more features that you can teach the machine to recognize and then it can classify, the better prediction rate you're gonna get at what is that morphological feature that is the ink. So no, that's correct. That's on the to-do list now.
Excellent. Thank you.
So correct me if I'm wrong, but if I understood well, basically whatever difference would be below your label of the letter can be recognized by the deep learning as an information. So what I mean is, even if you have no clue if it is a texture, if it is a relief, if it is absorption, phase contrast, whatever, as soon as there is any difference that you would probably never spot by eyes, the system can train on that.
Correct. That's what AI, regardless of application, cultural heritage, or specifically we're seeing this in medicine. That's where it's exceeding predictions by like radiologists in determining cancer, because it's just going to find things that we are not seeing.
So typically the thing is, if you can have more information, whatever it is, you will have better results. So did you already try to make, for instance, multiple energy scans? So you make several times the same scan, you change a bit the spectrum, because you will just have more information to give to your system.
Yes. Yeah, we did that a couple of years ago. So,
I think we did.
yeah, my colleague here's got more information. I think she can answer that.
We did different scans. Oh, I'm sorry. We did different energy scans when we scanned the samples at Diamond in September.
Okay.
So we're just beginning to process all of that data. But yeah.
Yeah. No, again, you're spot on too. Right now, we're at the point where the more information, the better for the deep learning approach.
Hello, thank you for the talk. I have a naive question because I'm not expert at all in neural networks. I would like to ask you, the learning set was on the left side of the fragment. I suppose it was Greek letters. But now imagine that actually it was a dictionary, and on the right you had Latin letters. Is there a bias?
No, because again, it's not thinking about alphabets. It right now at this level, it does not care. The only thing it's thinking about is, I understand what the substrate papyrus, what the fibers are, and what I'm looking for is a pattern in the data, which are these bumps. And so right now, it just starts to highlight that. So whatever the shape that results, it could be Latin, it could be Greek, it could be anything.
Could be a drawing.
Yeah, it could be drawings as well.
Okay, very, very interesting. Thank you very much, James. Well,